linear programming, it provides businesses and governments with a mathematical tool for determining the most efficient use of resources. Linear programming is used to solve problems in many areas of business, science, medicine, and the military by using a technique called the Simplex Method, which was developed in the 1940s by George Dantzig. In a linear programming problem, restrictions called restraints are represented with a system of linear inequalities. Okay, that's what we just worked on, a system of linear inequalities. When the system is graphed, a shaded region is called the feasible region is obtained. And that feasible region represents all of the solution points that satisfy the given constraints. So for each linear programming problem, we will obtain a formula of the form k equals ax plus by called the objective function. Okay, and in your classwork packets, you have this on page towards the end. You have this on page 46, everyone, of your classwork packet. And there's a lot of examples, too, that you can use to refer to. So page 46 in classwork. The objective function represents a model for the quantity, in this case k, that we want to maximize or minimize. For example, a typical objective function that might be used to maximize a company's profit, p, is given as p equals 3x plus 7y. And we find the maximum profit by substituting the ordered pairs x comma y of the vertices of the feasible region into the objective function to see which ordered pair yields the maximum profit. The fundamental principle of linear programming provides a rule for finding the maximum or minimum value of an objective function used in a linear programming problem. Okay, so here we have the fundamental principle of linear programming. So it's going to be about an objective function. Okay, so the objective function represents whatever we're trying to maximize or minimize. It could be you're maximizing profit, you're minimizing losses. You could be trying to minimize the number of hours that people have to work for you or something. You could be maximizing, what else? The output of the number of shirts you make or something. So the objective function is the thing that you're trying to minimize or maximize. Linear programming is a powerful tool for finding the maximum and minimum values of an objective function. Using the fundamental principle of linear programming, we are quickly able to determine the maximum and minimum values of an objective function by using just a few of the infinitely many points in the feasible region. Okay, and this fundamental principle, okay, I'm going to even zoom in on it if I can, is happening. So you can underline it if you have it in your own. It occurs at the vertices of the region. Okay, so that's the highlight thing. This maximum or minimum point is going to occur at the vertices of this feasible region. A vertex is like a corner. So that's where the solving systems comes into play, because we're going to look at where those lines cross. So just showing you here, this is representing the feasible region. So the vertices are the corners here, like 1, 7, 6, 7, 6, 6, and 1, 1. Those are the vertices of the feasible region. Those are the places where the maximum or minimum value can occur. So we're going to plug in those vertices. Let me give us something that looks like this. Quadrilateral. And they give us these points, 7, 4, 1, 1, 3, 8, 6, 11. Then our objective function is here. we don't know exactly what this function is about yet. We're just kind of doing the muscle work here. We're just doing the exercises to see what we have to do when we get to the real problem. So we want to find the max of k, so it could be a profit function, equals 3x plus y. So it has to be at one of these 4 vertices. Okay. So I like to create a table. So I'm going to use, say, the coordinate or the vertex. And we can write objective function. You can start at any of them, 1, 1. I'm going to go 3, 8. I'm going to go 6, 11. And then 7, 4. And the objective function is 3 times x plus y. I'm going to now copy that down for all of them. And I'll plug in the points. So here we have 1, 1. And we've got 3, 8. 6, 11. 7, 4. Okay, now 3 times 1 plus 1 is equal to 4. Here, 3 times 3 is 9, plus 8 is 17. And here we've got 18 plus 11, so that's 29. And here we have 21 plus 4 is 25. Okay, since we want to maximize this, you want to look for the maximum value. And so I see it there. So I can see that the maximum occurs at 6, 11, and it is 29. Okay, so both of them are, the coordinate itself and the actual value are important.